The Internet Control Message Protocol, ICMP, is a component of the Internet Protocol Suite, utilized by network devices like routers to transmit error messages and operational details signaling success or failure when communicating with another IP address. Unlike transport protocols like TCP and UDP, ICMP is not typically employed to exchange data between systems or by end-user applications, except for specific diagnostic tools such as ping and traceroute. A separate version, ICMP v6, is used alongside IPv6. ICMP, defined in RFC 792, is commonly employed for diagnostic or control purposes, with errors directed back to the source IP address of the original packet. ICMP messages do not have associated port numbers, unlike transport layer protocols like TCP and UDP. Many network utilities rely on ICMP messages, with examples including the traceroute command utilizing specially set IPTTL header fields and the ping utility using echo request and echo reply messages. ICMP operates at the network layer, corresponding to Layer 3 in the OSI model and Layer 2 in the Internet Standard RFC 1022 TCP/IP 4-layer model, or Layer 3 in modern TCP/IP protocol definitions. Although contained within standard IP packets, ICMP messages are often processed separately from regular IP data to generate appropriate error responses to the sending application. The ICMP packet becomes encapsulated within an IPv4 packet. This ICMP packet includes both header and data sections. The header immediately follows the IPv4 header and is distinguished by its protocol number, 1. Each ICMP packet consists of an 8-byte header and a data section that can vary in size. The first 4 bytes of the header have a standardized format, while the final 4 bytes depend on the specific type and code of the ICMP packet. The ICMP header structure is as follows. Bytes 003 correspond to type, code, checksum, and the 4 bytes following are designated for the rest of header, which is a 4-byte field with contents that vary based on the type and code of the ICMP packet. It is essential to note that ICMP error messages must not surpass 576 bytes in length. This data is crucial for the host to appropriately associate the message with the relevant process. If a higher-level protocol involves port numbers, it is assumed that they are located within the first 8 bytes of the original datagram's data. Control messages in ICMP packets are distinguished by the value found in the type field, while the code field offers supplementary context information for each message. Over time, some control messages have been deprecated since the inception of the protocol. Notable control messages include echo reply, destination unreachable, source quench, redirect message, parameter problem, timestamp, and various others. Each assigns specific type and code values for identification within the network communication framework. A source quench message advises the sender to limit the rate of messages sent to a router or host, which can be necessary when the buffer space is insufficient to handle the incoming traffic or if the buffer is near capacity. This occurs when data is transmitted rapidly from a host or multiple hosts to a specific router on a network. When the buffer reaches its limit, the router discards incoming data until there is space in the queue. However, without an acknowledgement system at the network layer, clients are unaware if the data reached its destination. Therefore, the network layer implements remedial actions known as source quench, where the router detects the disparity between incoming and outgoing data rates, prompting it to send an ICMP message to the clients to slow down the data transfer or pause for a specific period. This message assists in regulating the flow of data at the network layer. In contrast, an ICMP redirect message instructs data packets to take an alternate route, serving as a mechanism for routers to update hosts' routing information. For instance, if a host attempts to forward data through a router that redirects it to another router with a more direct path, the original router sends a redirect message to inform the host of the optimal route. As per RFC 1122, redirects should only originate from gateways rather than internet hosts. The redirect message includes the 32-bit address of the gateway for the redirection and details from the original datagram to match the reply with the request that triggered the redirection. Furthermore, the time-exceeded message is generated by a gateway when discarding a packet due to the time-to-live field reaching 0, or by a host failing to reassemble a fragmented datagram within the time limit. This message aids in identifying gateways along the path between hosts and is crucial for tools like traceroute. The message includes information such as the reason for the time-exceeded notification and details from the discarded datagram to assist the source host in matching it. Lastly, the timestamp message helps synchronize time across systems by setting timestamps on packets. The originating timestamp marks when the sender last handled the packet, assisting in time synchronization between hosts. Timestamp reply serves to respond to a timestamp message by including the originating timestamp, alongside receive and transmit timestamps on when the respective actions occurred. Although timestamp and timestamp reply messages were once utilized for clock synchronization, they have largely been replaced by protocols like the Network Time Protocol and the Precision Time Protocol for more accurate time alignment on the Internet. An address mask request is a message sent by a host to a router to acquire a suitable subnet mask. The recipient should respond with an address mask reply message. The structure of an address mask request includes fields for type, code, checksum, identifier, sequence number, and address mask. On the other hand, an address mask reply message is used to answer an address mask request with the appropriate subnet mask. The components of an address mask reply comprise of type, code, checksum, identifier, sequence number, and address mask fields, where type must be set to 18, code to 0, and address mask to the subnet mask. In instances where a destination is unreachable, such as where the physical connection does not exist, or the indicated protocol or port is inactive, a destination unreachable message is triggered. This message helps inform the client of the unreachability for various reasons, which could include issues like lack of a network connection, host unavailability, protocol or port inactivity, or the need for packet fragmentation, but with the don't fragment flag activated. Furthermore, a destination unreachable message contains fields like type, code, checksum, unused, length, next hop MTU, and sections of the IP header and original datagram data for contextual analysis. The type field specifies the error type, while the code field further details the reason for the unreachable destination. ICMP messages can also be provided with extra information via extension objects. Extensions in ICMP messages allow for additional information to be conveyed using extension objects characterized by a header structure comprising length, class num, C-type, and an optional payload area.